Okay, so this is going to be a video about the ideal gas law lab, and we are just going to I'm going to provide some guidance here. And know a number of you have kind of struggled with this lab. And so we'll go ahead and I'm not going to provide you all of the answers here, but I'm going to at least give you some guidance on each of these questions on to kind of what strategy to pursue. Okay. So the first question here is determine the number of moles of hydrogen required to react with 15.4 kilograms of oxygen. And we want the number of moles of hydrogen. Okay. So we're going to do a couple of things here. Let me get that pulled off to the side a little bit. Okay. So we have a couple of concerns. This is a basic stoichiometry problem. So the first thing we're going to need is a balanced equation for the combustion of hydrogen. And this one I'm going to help you out with. I don't know, it's simple enough, but we're going to do it. So we have this fact that two hydrogens combine with one oxygen to form two water molecules. And so there's our basic balanced chemical equation. And we're going to use that to convert these kilograms of oxygen into moles of hydrogen, or, find out how many moles of hydrogen would be required to combust with this oxygen. So the first thing we're going to do is convert that 15.4 kilograms into grams. And then we want to turn that into moles of oxygen. And in order to turn it into moles of oxygen, we're going to need to use the atomic mass off of the periodic table. The atomic mass for oxygen is 1 mole per 32 grams. It's 32 grams per mole, but you're going to want it in this form. You're going to use that to do a unit conversion to get from your grams to your moles of oxygen. Then you're going to turn it to moles of hydrogen by using the mole ratio that you're going to extract from that balanced chemical equation shown above. So you're going to say, well, hey, for every 2 moles of hydrogen, there's 1 mole of oxygen. You're going to put those into a conversion factor and use that to convert these moles of oxygen into moles of hydrogen. And then that's it. That is the answer to the question we're looking for. We were asked, well, how many moles of hydrogen? And so that'll answer it. Okay. For question number 2, this literally is something you're just going to look up. Okay. First off, you're going to look up what the vapor pressure of water is at this 23.1 degrees Celsius. And you're probably going to find out something, and I don't know this number offhand, I'd have to look it up, but something like 23 torr. And you're generally going to see it reported in torr, and we don't want it in torr, as the question specifies. We want it in atmospheres, because that's going to be useful for us in just a moment. So we're going to take these, and we're going to want to convert those into atmospheres. And your conversion factor for that is that for every 1 atmosphere, there are 760 torr. So use that conversion factor to switch ourselves into atmospheres. And then we can progress to the next question, which is about the partial pressure of the hydrogen present in a bottle. So this is a nice, easy problem. And what we're going to use is Dalton's law, which is that the total pressure in any system is just the sum of the individual pressures of whatever gases are present in that system. Okay, so that's the generalized law. In this case, we're going to say there are two gases present in the system. There's the pressure of the hydrogen, what we're looking for, and then there's this pressure from water. And that pressure from water is going to be your answer from the previous question. That's the vapor pressure of water. That is telling you how much pressure water vapor would exert at that particular temperature. So this one is known. You'll have calculated it in the previous problem. This is going to be your answer. And then for the total pressure, it's going to be, since we're doing this in an open container, well, kind of an open container, but the pressure that's put on the hydraulic trough is the same inside the bottle as it is in the trough. And so that allows us, sorry, my daughter was back there. That allows us to say that the total pressure is just today's pressure, which was your one that you looked up another couple questions ago. So this is going to be just found online. Okay, you're going to have your pressure there that's known from your previous problem, and you can solve your pressure of hydrogen. Now, you only a couple of things left to do here. Pretty easy at this point. Okay. So we're going to, actually, we'll use that piece, the backside of that same piece. Okay, now we're going to be asked to use the ideal gas law to determine the moles of hydrogen contained in each collection bottle. So ideal gas law is PV equals nRT. And we know all of these things now, or almost all of them, except for one. Okay, so the pressure, that's going to be your answer from the previous question. That's what you were finding. You were finding your partial pressure of hydrogen. Well, your pressure of hydrogen times its volume. And we know that these gas collection jars, you're told in the lab, since we weren't able to actually measure them, not 0.350 milliliters, 350 milliliters or 0.350 liters. And I suppose I shouldn't have done that conversion for you, but oh well, I did. N is the number of moles, and that's what we're looking for. R is that constant, 0.0821 liter atmospheres per moles Kelvin. And T is the temp in the lab, which you were told that I think I said 23.1 degrees C. Check the assignment. I just going off of memory there. 23.1 degrees C, but for any gas law problem, you need to turn that into Kelvin before you can plug it into the equation. Okay, so turn that temperature into Kelvin. Take your answer from the previous problem. Plug in your volume that you know. Plug in your constant that you know, and then solve for N, the number of moles. Now, what N is going to be is the number of moles per one bottle. And once we get that answer, whatever X is there, you'll get a number. I'm just not going to do the work for you. Once you get that, though, that can serve as a conversion factor to answer the final question. So what you know from your original answer to question number one is you need some number, well, I'll call it y. Again, I'm not going to do the calculation for you, but it's the answer from problem 1. Okay, and that answer from number 1 is going to be some number of moles. I shouldn't even put an X or an equal sign there, of hydrogen needed. And we can use this conversion factor that we just made, which says there are X moles per every 1 bottle, to turn those into the number of bottles of hydrogen. Now, this is going to end up, it should end up being a relatively significant number of bottles. This probably isn't a very realistic way to refuel your spacecraft. If you've got kind of, you should know at this point, I guess, that 1 mole of gas occupies a volume of 22.4 liters at standard temperature and pressure. And we're pretty close to standard temperature and pressure, so we would need 22.4 liters for every 1 mole. This bottle's about a third of the mole, about a third of a mole, or excuse me, about a third of a liter, which says that we would need somewhere about 70 bottles, give or take, to get 1 mole. So you could actually kind of work through this problem that way, and then using the combined gas law to adjust for the changes in temperature and pressure off of those nominal conditions at STP. But so there's actually a couple of ways to solve this problem, but this particular guidance will work. If you have any questions or get stuck on any of these steps, please hit me up on email or office hours so that we can kind of work through that together.